Yeah, and in the next subsection, we will see how to adapt decision trees to data streams by a very general concept, which is called the Höfting bound. Before that, we will have a short recap on decision trees. So you may recall we have given a training set, of course, of the features, the predictive features, and the class attribute, meaning that we have data observations, data objects with labels, and the goal is to find the function to predict the class label from a given observation. And the decision tree model is very simple. We have a tree model where the nodes represent tests on the predictive attributes, and the leaves contain the predictions on the class attribute. You see here that each node here is actually a test on one of the attributes, the predictive attributes, the attributes of the features of our observations. And depending on the outcome of this test, we will follow different subtrees. And in the end, we will reach a leaf of the tree, and in the leaf of the tree, we will find as pure classes or as majority decisions, some decision for a specific class. And you probably also recall the basic algorithm to construct the tree in a top-down recursive divide and conquer manner. So at start, all the training examples are at the root node. We select the best attribute for splitting using some purity measure, for example, information gain, Gini index, entropy, whatever, which is we determine the one attribute that splits the training data into the most pure partitions, and we continue in the subtrees with the actual partition of the training set that have the corresponding feature values. So if we split our data here, for example, according to A1 into two subtrees, which represent typically the values that are possible for A1, we will have only those guys that have this value in A1 in that particular subtree, and the guys that have this specific value F in A1 in this subtree, and so on and so on. So obviously the problem is that in order to decide which attribute to use for the splitting in a particular node, we need to have all the training instances resulting in this node. And we do that recursively, so we do that probably a lot of times, and this is obviously the essential operation for building the decision tree. And we talked about that before. So in data streams environments, the stream is infinite. We cannot wait forever in one node. We have to take the decision where to split, how to split, which attribute to split, or according to which attribute to split immediately, and we cannot wait forever, so to say, in a node. So the question is, can we make a valid decision in which attribute, or according to which attribute we have to split, just based on some data, not on all the data, because the decision tree should or would like to look at all of the data. The data is infinite, so we cannot look at the entire data. So the question is, how many data observations are necessary to make a valid decision for some split in some node? And yes, we can do that, and I told you before that that is based on the so-called Höfting decision, or Höfting boundary, and the resulting technique there are several variants of that, are called the Höfting tree family. So what is the Höfting bound? Well, the basic idea is, we want to pick the best split attribute for a node, and to do that, it may be sufficient to consider only a small subset of the training examples that pass through that node, because there are an infinite number of training examples, so to say. So we do not want to look at the whole data set, which is impossible in the case of data stream, but we just want to have a look on a small subset. And the problem is how many instances are necessary to make a valid decision. We talked about that on the previous slide. So we can use the so-called Höfting bound for that, for answering that question. So what is the Höfting bound? Well, very general, consider a real valued random variable with a particular range of values, which is denoted by the big R here, which is the maximum range typically. So for probabilities, the range is 1, so from 0 to 1. For information gain, for example, the range is from 0 to log 2 of C, where C is the number of classes and so on. Yeah, so the range is always from 0 to some specific maximum, which is denoted by this big R here. Yeah, and then suppose we have n independent observations of this random variable, and we compute from those n independent observations its mean, which is denoted here by R prime. So now the Höfting bound generally states that with a particular confidence of 1 minus delta, the true mean of the variable is at least R prime minus epsilon. Yeah? So the probability of that the real mean of the random variable, because we only have seen n variables. Yeah, the mean, of course, in order to compute the exact mean of the random variable, we should see an infinite number of observations from this random variable. Of course, we only see a sample of n observations, so we can compute the mean, but the mean will not be, of course, the perfect, is only an approximation of the real mean of the random variable. Yeah, and the Höfting bound states that the error we make by using this computed mean computed from the n observations from just a subset is smaller than epsilon with a given confidence of 1 minus delta. And we can even compute the error by this formula here. So it's square root of r squared, which is the range, the maximum range of the variable, times logarithmus naturalis of 1 by delta, and the whole thing divided by 2 times n. The n is the number of observations we look at. Yeah? So r is fixed, and if we fix the confidence interval or the confidence delta, and we look at n observations, we can even compute the error we make if we take this mean instead of the real mean. Yeah? So how does that help? Well, first of all, the bound holds true regardless of the distribution generating the value. So it doesn't care about being a Gaussian distribution or a Zipf distribution or a chi-squared distribution or whatever. Yeah? It only depends on the range of the values, the number of observations, and the desired confidence. This is cool because, yeah, it's model or distribution agnostic. The only disadvantage is because it's so general, it is a very conservative bound, and it is more conservative than a distribution dependent bound. But it holds true on the that is the downside. But the positive side is that it's distribution independent. Yeah? So anyway, how does that help? Well, now let's consider G to be the heuristic measure for choosing the split attribute. For example, G is the information gain or whatever, yeah, Gini index, whatever. Okay, and then let's assume that after seeing n instance at this node, we have x1 to be the best attribute so far with the best G value, information gain value, for example. X2 is the second best. And then we have other things like the third best, fourth best, and so on and so on. So third best and lower attributes have sufficiently smaller gains or smaller heuristic G values so that the probability of being the true best choice is negligible. So we have two attributes looking at, and the first one, the best so far after seeing n instances at a node, is x1, and the second best is x2. And we would like to be confident enough that x2 does not overtake x1 anymore, so to say. Yeah. So yeah, well, we could compute the delta between the two attributes x1 and x2. So g of x1 minus g of x2 is delta g. That is the difference between the values of the two best attributes. And now we take delta g as a random variable that will be estimated using the Hefting bound. That means we want to estimate the true mean, the true delta between those two from the observed mean. I mean, we have only looked at, say, n objects, yeah, and we can compute gx1 and gx2 after n objects, so we will have a delta g after n objects. And now we want to estimate the error of delta g after n objects with respect to the true delta g, which will be after an infinite number of instances. Yeah, so in this scenario, the Hefting bound states that the probability of that delta g from after n observations minus epsilon is smaller or equal to the real mean, meaning that delta g, the computed delta g, the error we make with the computed delta g is smaller than epsilon, with a confidence of 1 minus delta, and the Hefting bound can be computed as before. Yeah, so that the error can be computed as before. So well, we know the range, and for a given delta, the only thing depends on this 2n here, and n is the number of objects we have to see in order to get this epsilon. Yeah, so n is actually the thing we want to know. How many n's, how many observations should we look at in order to be to have a good estimation, so that delta g prime here is a good estimation of the true mean of delta g. Yeah? So for a desired delta, we can compute the corresponding Hefting bound epsilon. Yeah, computed after seeing n observations. So everything is fixed. We have looked at n observations. R is fixed. Delta is fixed. So we can compute the epsilon. Yeah. And now the Hefting bound guarantees that we have this equation. So if delta g, which is computed from gx1 and gx2 after n observations, is, so if the delta is above epsilon, we know that the true difference is greater 0, because we have this inequality here. Yeah? This inequality comes from the Hefting bound with confidence 1 minus delta. Delta is fixed. So if we just take plus epsilon here, we have this one here. So the difference is obviously greater 0. So the first attribute is obviously better than the second one. So we can use x1 for splitting at the node with a confidence of 1 minus delta. So this is the fuzziness still, yeah, but with a confidence of 1 minus delta. Otherwise, if delta g prime is not greater or equal than epsilon, so is smaller than epsilon, the sample size is not enough to do a decision with a confidence of 1 minus alpha. So the decision is not stable. So far, we cannot guarantee that we can choose x1 with a given confidence. Yeah, because with r and d fixed, the only variable left to change epsilon is n. So we have to sample more points or observe more points, more observations at the node, in order to increase the delta g prime. Yeah. In order to reduce epsilon, of course, delta g prime will also be recomputed, of course. Yeah. Okay, and we need to extend the sample in that case by seeing more instances until delta g prime becomes larger than the corresponding epsilon. So delta g prime and epsilon will change if we look at more instances, obviously. Yeah. So that's the idea, using the very, very general Hefting bound in order to estimate if we can do a proper or stable decision or not.